All right. So yeah, it's 8:35. So I'm going to get started. This is COMP2804, Discrete Structures 2, and I'm the instructor, Daryl Hill. So I guess about test 1. So Brightspace has some sort of design thing. So the grades were hidden for test 1, but the category was not. So the test category was not hidden. The grades for test 1 were hidden because I hadn't finished marking the PMC ones. The grades were uploaded, so you could see your grade because the category grade summed it up, and it was only the one item, so it was visible, which that's a strange design choice. But so I hit it, but now they're back up. So if you do not have a grade, then you are one of the about 5 people that for some reason the Scantron didn't get your name or student number. So just send me an email. I'm going to be looking through them today. I have a stack of 500 Scantrons that I have to search through. But yeah, so if you do not have your mark should be visible, and if they're not, or if you don't have one, just email me and we'll get it sorted out. All right, so, and that sort of brings us to today's topic, because I have 500 Scantrons and a bunch of people want to come and see their Scantron. So the question is, should I just leave them unorganized, and then every time somebody comes, I leaf through? On average, I'll probably have to look through 250 of them to find somebody. Or should I sort them? If I sort them, if you sort by hand, you probably use a version of mergesort. It's probably the easiest one to do by hand. So, and then, so how much work am I doing if I sort it? And how much work am I doing if I just use a linear search on an unorganized pile every time somebody comes in? And what's the break-even point? So we're going to be analyzing today mergesort. We'll be learning a little bit about, we'll be using some of the tools that we already know, but we will also be learning about a new technique called unfolding. But yeah, so yeah, that's, I'm pretty sure I'm going to be sorting them today. So if you do want to come talk about your test, maybe wait till next week. I think it'll take me an hour, maybe 2 hours. I don't know. We'll see. And then, yeah, so by next week, I should be all set for whoever wants to see their Scantron, if you feel there's some sort of problem with your grade. But yeah, so that's where we are today. On the 10th, we're doing mergesort. This is the last lecture on recursion. So after today, you should be able to do all of the assignment. But yeah, any questions before we get started? Okay. All right. Oh, well, I'm in the wrong spot. Okay, so we're gonna do analyzing more recursive algorithms today, in particular mergesort and probably binary sort. And then halfway through, I got a little demonstration of sorting algorithms. That's kind of fun. But yeah, so how does recursion fit into this class? I guess might be a fair question, but basically what we're doing is counting, right? But we're counting. Well, analyzing algorithms uses a form of counting, and analyzing recursive algorithms uses a form of counting, and that all comes from recursion. So when we're analyzing an algorithm, we're counting significant operations. And then what we do is we take whatever our pseudocode or actual code is, we look at these significant operations, whatever we think should be appropriate for, basically whatever happens the most or whatever takes the most time, or usually both. And then we derive a recurrence, which is just a recursive function. And then once we're at that point, we have some tools to find a closed form, but today we're going to learn another tool to find a closed form, which is unfolding, which is slightly more reliable than plugging in values and trying to guess what the closed form might be. All right, so we're going to analyze mergesort. First, we're going to talk about what merge sort does, and then we will make up some pseudocode, and then we'll analyze it. And yeah, so we're going to, our significant operation for this will be the number of times we have to copy an element to a new location. And the reason I chose that is because when I'm doing merge sort, I will be moving scantrons here and there, and I want to count about how many of them I have to move. So that's what we'll be sort of simulating that with our algorithm. And yeah, then to find a closed form, we're going to use a new technique called unfolding. Okay, so the idea behind merge sort is, again, we're going to use the power of recursion. We talked about how we can design algorithms without really knowing the solution, as long as we know in the simplest case how to solve it. And then if we know in a smaller case, if we assume that we can solve that smaller case, and we can use that solution to solve the bigger case, then we can use recursion. And then everything else just sort of follows by magic, or not magic, but. All right, so in terms of sorting, we have to figure out a base case for our sorted list. So how do we sort a list of length 1 or length 0? Well, fortunately for us, that comes pre-sorted. So in the base case, we know how to sort a list of elements. So if it's size 1 or size 0, it's already sorted, so the base case is fine. Now we want to figure out a recursive algorithm. So what we're going to do is, we're going to divide our list in two and recursively sort each half. All right, so this is a technique known as divide and conquer, where we break down a problem into smaller and smaller problems, solve those smaller problems, and then recombine the smaller problems to solve the bigger problem. All right, so more generally, it's called divide and conquer. It's also a example of recursion. So we have a sort algorithm that sorts. Let's see. So I have there was a bunch of mistakes in these slides that I thought I corrected, and there's still this one. That should say list. For the number of hours I stared at this and could not see that this said item instead of list, this should be list. And this is the size of the list n. So in the base case, if I have a list of 1 or 0, then I just return that list, it's sorted. Otherwise, I'm going to copy half of the list into a new list called left, and I'm going to copy the other half of the list into a new list called right. All right, so I have my list of however many items, and I'm just going to divide it in half as best as I can. And then I'm going to copy these into the left-hand list and these into the right-hand list. Okay, so I've divided my problem now, and now I'm going to conquer these smaller problems. But what I'm going to do is conquer them recursively. Again, we're making an assumption here. We don't know if these recursive calls will work. But if we show we have a base case, and then we show that, well, if we assume that we can solve these and then use those solutions to reconstruct or to solve the bigger problem, then our recursion works, right? It's sort of like dominoes. I have the last domino, and I have, well, yeah. I guess my analogy is falling apart here, but it does work if I could think of it correctly. But yeah, so recursion is like dominoes, same as induction. So we're going to, by our inductive assumption, these calls to sort work because they're on lists half the size. Okay, so up until now, when we were doing recursion, we were looking at lists of, we assumed it worked for size n minus 1. So this is known as weak induction. But you can do what's called strong induction, which is where we just assume that something works on a list size, any size less than n. So in this case, it's n over 2. But yeah, you have to be a little bit careful with it, but this does work out, and we'll, yeah. Okay. All right, so now we want to turn these sorted lists into these two, half half lists that are both sorted. I want to turn that into one sorted list. And then if we do that, we've proven that merge sort works. We have the base case, we have the recursive case. So yeah. How do we take two sorted lists and turn them into a single sorted list? Well, I guess the clue is in the title, right? We're merging two sorted lists, so we're just going to stick them together. So I have two sorted lists here of length 4, and I want to merge them into a single sorted list of length 8. So how am I going to do that? Well, I start by looking at the two front elements. I know these are the least element in both of these lists. I compare them together to find out which is less than the other, and that one I copy to the front of my list. So in this case, 1 is less than 2. I copy 1 to the first position of my sorted list. I update this pointer to point at the next item in this list, and then I repeat. I compare them again. So I compare 2 and 3. I see that 2 is smaller, so I'm going to copy 2 down into the next position. Yes. I copy 2 down into the next position. I update this pointer now. And now I have 2 pointers pointing to 3 and 5. I compare those. 3 is less than 5, so I'm going to put that in the next position. And I'm going to update this pointer. I compare 4 and 5. 4 is less than 5, so I'm going to copy that down and then update that pointer. 5 and 6 are compared. 5 is less than 6, so I put 5 here. 6 is less than 8, so I'm going to copy 6 down next. At this point, I run off the end of this list. I still have 8 and 9 over here, so I simply, at this point, I can just copy them both down. Those are, I know, are in sorted order, and everything else is less than them, so they can safely go at the end. So quite a simple algorithm, but you know, it does the job we're looking for. Is we took 2 sorted lists of whatever length, and we merged them into a single sorted list of, you know, the size of list 1 plus the size of list 2. All right, questions on that? Okay. All right, so finally we have a sorted list. So we're going to take a look at this merge algorithm, and we're going to give a rough approximation or count the number of times we copy something when we perform this. And then we're going to use that analysis later in our merge sort algorithm. So just in terms of merge, we're going to write out the pseudocode. So merge left and right. I'm going to have, I set my 2 pointers, J and K, both to 0. So these are the beginning of left. J is pointing to the beginning of left. K is pointing to the beginning of right. I'm going to make a for loop. So I takes on the values from 0 to the length of the left-hand list plus the length of the right-hand list. Right, so I know I have to iterate at least that many times. And then I'm going to compare. So J is the pointer, the current pointer to left, and K is the current pointer to right. So I grab those values, I compare them, and I see which one is smaller. If left is smaller, then I copy this into, again, I use item instead of list, but this should say list. I represents the next available position in this list. So I copy that element in there and I increment that pointer. Otherwise, I know that right is less than left. Well, they could be equal also, but if they're equal, then I copy one arbitrarily. It doesn't matter which one. So I copy right. K is the current position of right. I copy that into the next position of the list, and I increment the K pointer. Right. At that point, you know, once I'm done the for loop, I can return everything. So I skipped, just in the interests of keeping it simple, I skipped the case if one of the pointers runs off the end of the list. Okay, so I should have, just to keep it simple, I put it like this, and asymptotically it makes no difference, right? I'm still copying the size of left plus the size of right items every time I perform a merge, regardless of whether or not I run off the end of one list or not. Okay, so yes, the for loop executes the length of the left plus the length of the right times. Every time it executes, I either copy the left-hand item or the right-hand item into my list. So that means I've made length of left plus length of right copies. This is what happens when you make a lot of last-minute changes to your slides, is that sometimes you make mistakes. But yeah, so length of left plus length of right copies are made in the merge. Okay, any questions on that? Okay. So yeah, and this is basically the sum of the lengths of both lists. So we have a rough idea now, well, not even a rough idea, a pretty exacting idea of how many significant operations are performed during a merge. And we have successfully taken two sorted lists and made it one big sorted list. So our induction works. So now we have a complete idea for sorting. We have a base case, we have the recursive case, and if the recursive case works, then the whole thing works. So I divide my problem in half until it is a manageable size. So yeah, in pseudocode, my sort algorithm is I divide my list into two lists of length, ceiling of n over 2 and floor of n over 2. If n does not divide evenly, then one list will be slightly bigger than the other, but that's okay. We sort the sublists, and then we merge them into a single sorted list. So this is known as divide and conquer, and it's also a recursive algorithm. Of course, the recursion part is when we sort, we just call the original sorting algorithm again. Okay, so that's at a high level, and the sort on the shorter list works because of our inductive assumption. All right, so we'll go over a sort of a complete practice run of merge sort, just so you just to sort of flesh out all these ideas. But any questions on what the algorithm is or anything else? Okay. All right, so we have here an unsorted list, and we're going to perform merge sort on it and just show you what happens at each stage. So at each step, to start with, this is a call to sort on this list. All right, so what it does is it copies all of these elements. I make two lists, a left and a right, and I simply copy half into each list. And 5, 2, 9, 8. In a very straightforward manner. I don't reshuffle them or anything else. I just make straight up copies. And then from here, I call sort recursively on these lists. Okay, so yeah, there's my two lists. I call sort on left, sort on right. And again, well, the size is still greater than 1. So I'm going to recursively call sort on these. So I'm going to first copy, split up these lists into two sublists, left and right, in a very straightforward manner, and recursively call sort on both of them. Okay. At this point, in each of these calls to sort, I still have a list that's not, it's still greater than 1. So I'm going to recursively call sort again. So yeah, I split the lists up. I recursively call sort on each of these. These recursive calls to sort all return immediately, right? Because each of them is called on a list of length 1. So at this point, I'm at the bottom of what we call the recursion tree. And then it's going to, I'm finished, I'm at the leaves, and then, well, in the merge sort, we come right back up the recursion tree and then start merging. Okay, so two things are happening here. We're demonstrating merge sort, but we're also, when you write recursive algorithms in general, you can break it down in what we call a recursion tree, which is sort of keeps track of how many recursive calls you make in total. Okay, so how many times do we make, in this entire recursion tree, how many times do we copy an element? Jeez, capital N. All right, so I missed that one. Should be small n, but this is, so we say that our list is of length n, right? So in this case, n is a value 8. I have 8 items in my list. So how many copies do I make in total? Well, in the first call to sort, I have to split it in 2. So I make n copies, right? So 4 copies over here and 4 copies over here for 8 in total, or in general, n. If I look at the next level of my recursion tree, right, these are 2 separate calls to sort, but if I add up together how many copies they make, well, you know, here I made 2 copies, here I made 2 copies, here I made 2 copies, here I made 2 copies. If I total those up, I get 8 again. And in general, I still have n, right? I still have all of my elements at that second level of the recursion tree. So again, I'm making n copies. So n here, n here. Now I can look at the next level. I made 1 copy here, 1 here, 1 here, 1 here. If I add all of the copies up, these are separate calls again, but they're all at the same level of the recursion. If I sum them up, I have again made n copies. Okay. And then finally, at the leaves, I just return. I don't make any copies, so there's 0 here. So what this does is, this is not a proof of the runtime, but this is useful in seeing if you have a recursive algorithm, it's useful to figure out how many operations you're doing in total. All right, so you can use this as sort of a sanity check. So in this case, I make n copies at every level. So the real question is, how deep does my recursion tree go? How many levels are there as a function of n? Okay, so that's what we're going to figure out. So now if we start back at the bottom and then work our way back up the tree. So once we've sorted these lists, right, at the leaves, they are returned. And then I start the merge operation, right? So I call merge. This would be level 3. Well, actually, let's say this should be level 3, but at level 3, these 2 items are returned, and then I merge them into a single sorted list. So in this case, the 4 goes here, and the 7 goes here. And this was, yeah, on this call to merge. I had, you know, I called sort on this and then sort on this. When these return sorted lists, I call merge on both of them. Again, 1 goes here and 6 goes here. So I've made, you know, 2 copies there. These are returned. I perform my merge algorithm. The 2 goes here, the 5 goes here. And for the last one, the 8 goes here and the 9 goes here. Okay. So now I'm at level, what is this? This is level 3. Now at level 2, the sorted lists from level 3 are returned to me, and I'm going to merge them. Now you can sort of see the algorithm in a little more clarity, but I have my 2 pointers to left and right. I compare the, you know, the 1 to the 4. The 1 is less than 4, so I put the 1 here. I update this pointer. I compare 4 to 6. 4 is less than 6, so I put the 4 here. I update this pointer. I compare 6 and 7. 6 is less than 7, so I put the 6 there. This one is done, and I copy the 7, and then everything is done. Okay, so this is a call to merge on these 2 sorted lists that were returned to me at this stage of the recursion. All right. And then I keep doing this. So here I have 2, and then 5 is less than 8, and then I've exhausted this list, so I can copy 8 and 9 down here. Yeah, and so I'm working my way back up the recursion. Finally, at level 1, my first call to sort, I made these 2 recursive calls. These lists were returned to me sorted, and then I'm going to do the merge step. So 1 is less than 2, 2 is less than 4, 4 is less than 5, 5 is less than 6, 6 is less than 8, 7 is less than 8, and then I'm left with simply 8 and 9. Okay, so that is merge sort, sort of a short example in its entirety. But, yeah. Any questions on that? Okay. Final sorted results. Again, we're going back up the recursion tree. We can again count how many copies are made, right? So as we are merging these, right? So I make 1 copy here at this stage. Then I make another copy, then I make another copy, then I make another copy. If we count up all the copies that are made at a certain level, well, nothing happens at the leaf. But when we get to level 3, I've had 1 copy, 2 copies, 3 copies, 4 copies, 5 copies, 6 copies, 7 copies, 8 copies made. So again, 8 here, and in general, n copies are made coming back up the recursion tree now. At the next level, it's the same thing, right? I merged these. So I've made 1, 2, 3, 4 copies here, and 1, 2, 3, 4 copies here for 8 total. And in general, I would have n copies at this level of the recursion tree. These are not happening at the same time. It's not parallel, but it's useful to group them together. Finally, at the last level, I again make 8 copies, or n in general, as I merge them. Okay. So we sort of have a rough idea of how many operations we make. So we make n copies going down and n copies coming back up. So it's going to be about twice the depth of my recursion tree, right? Give or take a little bit. Okay. So yeah, this is my pseudo code, but let's change that into actual code. We're going to take our algorithm from before. So in our base case, if the list has size 1 or less, we return, we're done, we don't make any copies. Otherwise, we copy half into the left-hand list and half into the right-hand list. We sort those individual lists, and then we call merge on those 2 lists. This merge we looked at earlier. So yeah, it's the amount of work done here is the length of left plus the length of right. Okay, so that's our entire pseudocode now. And now, as we did before with, what was it, the messaging problem and the towers of Hanoi, is we can analyze it. All right, so to simplify our analysis, we're going to assume that n is a power of 2. So it always divides evenly. All right, so how many copies do we make to split an array of length n in 2? Well, we've made n over 2 copies in this line and n over 2 copies in this line. If we add those up, we made n copies altogether. This is for a single call to sort, right? So our idea here is, again, we're going to devise a function. We're going to call it T of n, and this is the number of copies made in a call to sort n. Right, or list of size n. So in this single call to sort, we've made n copies here. In our merge step, we know we've made n copies, right? So it's the length of left plus the length of right.
Together they make n, so there's n copies here. Plus whatever happens in my two recursive calls. Okay, so I split my array in two, that's here. I merge my two arrays of length n over 2. That happens in the merge step here. So those are n copies plus n copies. So I have two n copies, not including the recursion. So if I let T of n be the total number of copies to sort an array of length n, I can express it as T of n is equal to, well, this is the splitting and the merging, plus one recursive call to the left-hand side and one recursive call to the right-hand side, both on lists of size n over 2. All right, so again, conceptually, it's the same as the algorithms we analyzed before, slightly more to it, a little more complicated, but we have now a recursive function that tells us how many copies we make in this call to merge sort. All right, questions so far? Okay. All right, how are we doing for time? Okay. Okay, so here's our recursive function. Now we want to analyze it. We're going to use a new technique called unfolding, right? So what we did before is we just plugged in some values. We saw how the values were changing. We made a guess. We're still making a guess, but it's going to be a more reliable one. So I'm going to take my recursive function. I'm going to gather up my two like terms here. So I have 2 times T of n over 2. Well, what is this T of n over 2 equal to? Well, what I'm going to do is I'm going to basically take my original recursive function, and I'm going to do a find replace everywhere where I see n. I'm going to replace it with n over 2. So I have T of n over 2 is equal to T of n over 2, but I'm replacing that n with n over 2. So I get n over 2 over 2 plus T of n over 2 plus 2 times n over 2. Okay. And then, well, T of n over 2 is simply T of n over 4. So that's I skipped this intermediate step here, but that is, I'm just taking this original one. Everywhere where I see n, I replace it with n over 2. So I get this expression for T of n over 2. Okay, and then I gather like terms. So now I know my T of n over 2 is equal to this. Okay, so now I'm going to plug that back into here and then do a little bit of algebra to make it look a lot nicer. Okay. Yeah, all right, so I plug that in. So I've replaced this with this here. Now I'm going to distribute this 2 over these two terms. All right, so I get 2 times T of n over 4 plus 2 times n over 2. That's here. And then I'm going to include this term here. Okay, if I multiply this out, well, this 2 and this 2 cancels out. So this is just left with 2n. Okay, so I have 2 times T of n over 4 plus 2n plus 2n. Okay. Questions? Okay. There. And yeah, so that's what we have at this point. Now, again, I have this purple term. Again, I can plug in this n over 4 into my original recurrence. So anywhere I see n, I put an n over 4, right? So I have, well, n over 4 over 2 is equal to n over 8. So for these two, the n over 4 over 2 simplifies to n over 8. Plus 2 times n, I replace the n with n over 4. I get 2 times n over 4. I collect the like terms, and again, I have 2 times t of n over 8 plus 2 times n over 4. All right, so now I can plug this back into here. And again, this is going to be 2 times 2, now it's times 2, t of n over 8 plus 2 times 2, right? So I'm multiplying this times this part now. So that's times 2 n over 4 plus, and then I can append these on. Right, so it starts out looking ugly, but once you do a little bit of algebra and work it a little bit, you start to see a pattern emerging, and then it gets easier to write the next one once you recognize the pattern. So what we're doing here is, well, this, if I look at this term here, well, this 4 is, basically 2 times 2, so that cancels out there. And now I have, for this term, if I simplify, I get another 2n. So I have 2 times 2 times 2, which is basically 8, times t of n over 8 plus 3 of these terms. All right, so good questions. Yeah. All right, so that's a good question. So what we're trying to do is recognize the pattern. Once we think we found the pattern, we can jump to the end, right? So what we're going to do at this point is say, well, I'm going to assume my recursion is over after k steps. And then what I'm going to do is solve for k. But if I assume it's over after k steps, well, this is, I could have rewritten this as 2 to the power 3 times t of n. This 8 is also 2 to the power 3 plus, and this is 3 times 2n. So in this case, in the third step of my recursion, my k is equal to 3, right? But then after k steps, I'm going to replace all of these 3's with k's. So I get 2 to the power k times t n over 2 to the power k plus 2 times n times k. Okay, and that's, I just assumed, I know my recursion ends, it has a base case. So I'm just going to say, well, it ends after k steps. And then I'm going to figure out what k is. All right. Questions on that? Okay. So at this point, I have a pattern. I have now a variable. I want to figure out how deep my recursion tree goes. So how many steps until we evaluate the base case, right? So the base case is t of 1 in this case. We're assuming that n is a power of 2. Otherwise, it would be t of 1 or t of 0. So yeah, at what point in this pattern do we get t of 1? Well, that's when this is equal to t of 1. Okay, so I want, this ends, I know, at, or I assume it ends at t of n over 2 to the power k. What I know is that this actually ends at t of 1. Okay, so what I know is that n over 2 to the power k is equal to 1. That's when my recursion ends. All right, so now I can solve for k. I have n equals 2 to the power k, right? I multiply both sides by 2 to the power k. Now I want to find k. I can take the log base 2 of both sides. So I'm not going to write the base 2. I'm just going to write log, just to make things easier. So, and just a little. So if I have a log to the base 2 of 2 to the power k, well, what that's asking is, it's log to the base 2. So I'm asking, well, how many times do I divide this by 2 until I get down to 1? That's sort of what log does. Well, I mean, it's actually exactly what log does, but there's other ways to phrase it. So how many times can I divide 2 to the power k by 2 before I get to 1? Well, k times, right? That's, yeah, so this is equal to k. So a log base, whatever, log base a of a to the power whatever is whatever. A to the power x is x. So in this case, I take the log base 2 of both sides. I have k equals log n. So that's how deep my recursion tree goes, is log n. All right, is that good? Questions on that? Okay. All right, so I've solved for k. I can plug that back into my closed form. There we go, we're doing good. Let me erase all that. So yeah, I know this ends at 1. If I plug k in here, I get 2 to the 2 to the power k. This is actually 2 to the power k as well, so that equals 1. And then I just substitute in here my k value, which is equal to log n. This is what we did earlier. Take the log of both sides. So I have n times t of 1 plus 2n times log base 2 of n. Okay. At this point, what is t of 1 equal to? Well, if n is equal to 1, I make no copies. I simply return the sorted list. So this is equal to 0. So this term becomes 0. And then the whole thing is 2n times log base 2 of n. Okay. So we did what we did before is we had a recursive function, which is not written here, but we did have one. We derived it from just analyzing the algorithm. We wanted to find a closed form, but it was a little more complicated than if I started plugging values in, they're going to get really big really quickly. But using unfolding, I found the pattern. I assumed the pattern ended after k steps, which allowed me to, put values to all of these, and then I could solve for k because I know where my recursion ends. Once I solve for k, then I simply complete this, and I get the, now I have a guess at my closed form for t of n. Okay. All right, so then the next step is, well, as we've done before, we're going to verify by induction. Right. Questions so far? Yeah. On a test? Probably not. I mean, you could, if it's multiple choice, right? So you can use this for sure. If you have a calculator, that would also work. You could just plug values in and check them, right? So yeah, this is an assignment thing. I would have to figure out how to wedge it into a test. I don't know. Yeah. But yeah, maybe. Okay, other questions? All right. Okay, so we have a base case, recursive case. We have a guess at our closed form. So now we want to verify using induction. So our base case t of 1, I'm going to plug 1 in here. So t of 1 equals 2 times 1 times log base 2 of 1. Log base 2 or log base anything of 1 is 0, right? How many times do I have to divide 1 until it's equal to 1? How many times do I divide it by the base until it's equal to 1? Well, 0, it's already 1. So this is equal to 0. So our base case holds. So now our recursive case, oh wait, I'm sorry, I think this, yes, that's equal to 0. Now we do our recursive case. So our inductive hypothesis is, of course, we assume that our recursion works, right? So what that means is that we assume that this closed form is true for some value that's less than n. In this case, n over 2. All right, so we assume this is true. We're going to plug these values into our recursive form and then do some algebra that looks a lot worse than it is. I have t of n equals 2 times t n over 2 plus 2 of n. I simply gathered like terms from here. Now I have this, and I'm going to plug in my inductive hypothesis. So that is equal to 2 times 2 times n over 2 times log base 2 of n over 2. And then plus 2n. Okay. All right. So now what happens here? Again, we're going to talk a little bit about what happens with logarithms when you divide. So if I have a log base 2 of a over b, that is equal to the log base 2 of a minus log base 2 of b, right? And that applies to any base. So that's just how logarithms work. It works the opposite for multiplication. If I had a times b, then this would be a plus. So that's a little bit about how logs work. Now, if I expand this out, well, I can do a little bit of canceling here. I get 2 times n times log base 2 of n minus log base 2 of 2 plus 2n. Log base 2 of 2 is 1, right? I divide it by 2 once to get to 1, so I can substitute 1 in here. And now I'm running out of space a little bit, but I get 2n log base 2 of n minus 1 times 2n plus 2n. Well, these cancel out, and I'm left with 2n times log base 2 of n. All right, that's good. Questions on that? Okay. So yeah, I have all of the same thing here, slightly neater, and it actually fits on the page. All right, so I know my merge sort algorithm runs in 2 times n. If I'm sorting a list of size n, it's 2 times n times log base 2 of n. All right, so I have 500 scantrons to sort. 2 times 500 times log base 2 of 500. So log base 2 of 500 is, anybody know? So 512 would be the closest. So the log base 2 of 512 is 9, I think. I think it's around 9. So this would be 2 times 500 is 1,000 times 9 for this one, about. So that's about 9,000. 9,000 times I have to move the Scantron sheets across my desk. All right, so for those of you that come in, if I'm looking for your Scantron, there's 500. If I just keep it unorganized and flip through, it would take me about 250. I would have to look through about 250 on average before I found yours. All right, so the break-even point is when these are equal. So if I have about 36 students come in to want to look at their Scantron. Now this is, of course, not quite accurate. I could probably sort a little bit faster than that, but yeah, if I have more than 36 students who want to see their Scantron, I should sort them. If I have significantly less than that, then I'll probably just flip through. But who wants to see their test? Nobody. All right, maybe I'll save myself some work this afternoon. Okay. Yeah, is that good? Any questions? All right, so you guys have been very attentive. Let's look at something a little more lighthearted. We'll get back to the rough stuff after, but for now, there's a visualization. Oh, I have to see, which one are we doing? Selection sorter. So I'm just going to change that to merge sort. So this is a visualization of merge sort written in Java by Robert Collier. All right, so he's the one who wrote this. I just borrowed it. Well, we taught the same class once and we used this, so I've kept it ever since. Okay, so it sorts it, it computes it, it gathers a bunch of data, it returns the data, and then we use that data to simulate what happened during the sorting. So this is merge sort. What you're going to see is that, well, I'll explain after we see what happens. I'll explain what this is visualizing, and then we can look at it again. But yeah, basically it's, so you can see sort of the merge operations happen very quickly. So it's going down the recursion tree. Every time it, I could actually draw it on the board. Yeah, so at the end, the merge happens very quickly. But what happens is we have, of course, if we draw out our recursion tree, so we split this into two. Let's just make some very simple looking tree. So how we looked at it is we assumed sort of everything happened at once, but what actually happens is that, of course, we make the call to sort left. And then this call makes a call after it splits it, it makes a call to sort left. And then it splits it, and then this makes a call to sort left. So we get all the way down to here, we come back up, it makes a call to sort right. Nothing else has happened. This returns, I have two sorted lists, they get merged here. That's where we see a little bit of action happening. Now this is sorted, we jump back up here. Now this calls sort right. This goes down here to sort left, it returns, goes down here to sort right, it returns, it merges. This is again where we see some action. Now this is sorted and this is sorted. They're both returned. Now this gets sorted, so now you see the bigger jump. And then it starts to go down into the right-hand tree and does the same thing. So then you see a little action here, it goes up, you see a little action here. When this returns, you get a big merge and then another big merge. And that's why the ending comes together very quickly. But yeah. Yeah, so, you know, you can kind of see where the small, so it's 1,000, I think it's 1,024 picks like squares. They're shuffled and they're each sort of labeled from left to right, you know, 1 to 32, and then there's 32 rows. So yeah, it goes down, it does a little bit of action here, a little bit of action here, and then it merges them together as soon as it can. And then at the end, you get everything comes together, boom. Right. So the other thing we've seen in this class is quicksort. So quicksort's not quite as dramatic, but so you kind of have to make design decisions in this because it returns the data. Now I have to figure out, well, how am I exactly going to represent this? So if you remember quicksort chooses a pivot. Let's say we have this, it chooses a pivot P and it takes, it looks at everything and puts all of the things less than P over here and all of the things greater than P to the right. And it does that recursively. So in terms of this tree, you know, we get to here.
once we get to here, these are sorted and in their correct location. So you can see it gets built sort of from the top down in this case. But it's really just, once we get here, this is sorted. Once we figure that out, this is completely sorted. These are all in their correct spot right off the bat. So it gets built a little bit differently, but yeah, we'll look at quicksort again later. So just another couple fun ones. If you're familiar with bubble sorting runs slower, but you know, since we're here, we might as well look at it. What a bubble sort does is, if I take my list, it's n squared. I start at the beginning and I just look at every pair of elements, and if they're out of order, I swap them. Right, so if there's 3 here and 2 here, I just exchange them. And I keep going down, and then I go over the entire list n times, right? If the list is size n, I do this n times. And what happens is that the large elements, so if I go through, the first time I go through the largest element, as soon as I find it, I will always swap it until it gets to the end. Let's say it's 9. So after the first pass, 9 will be in the correct location. After the second pass, the next largest element will be in the correct location, and the next. So that's basically how that works. But yeah, so you can see that in action. Yeah, so everything's getting bubbled up to where it's supposed to be. Which in this case, the highest numbers are at the bottom, but and it runs significantly slower, right? This is big O of n log n for merge, and bubble is big O of n squared. Yeah. All right. And then there's sort of the, again, since we're here, selection sort is, it's also an n squared algorithm. What it does is it goes through the list n times again, but every time through, it says, well, I want to find the smallest element. So it goes through and finds the minimum. Once it gets to the end, it takes that minimum, it remembers where it is, and it swaps it with the first location. Right, so if it finds 1 here, or let's say there's 2, then it'll swap, after the first pass, it swaps this one and puts the 2 over here. And then it does another pass, it finds the 2 here, that's the smallest it's seen. So after that pass, it swaps these 2. So that's what do we call it? I always mix it up with insertion and selection. They might be the same, but I can't remember. So yeah, now it's being built from the lowest place, and you can see it's just picking out individual squares and then popping them into where they're supposed to be. So there's not a lot of movement like bubble sort, but still takes a long time. Yeah. All right. Any questions on any sorting? You guys should, as computer scientists, sorting algorithms should sort of be second nature after a while. But all right. All right. So that was our nice little interlude. Yeah. All right. So we'll talk a little more about, so that was merge sort using unfolding. This is kind of difficult. We'll do another example, binary search. So this is also apropos because once I sort the scantrons, if anybody wants to come in now, I'm going to do a binary search on that the sorted pile, right? So you come in, you give me your name. I look at the first letter of your name, and then I jump about halfway if I don't know the distribution, or if it's, So I look halfway and I see somebody's name, and your name either comes before or after it. And if it comes before, then I can throw away all the large ones. If it comes after, I can throw away all the small ones. And then I repeat on half of the pile, right? So that is sort of the idea behind binary search, which we'll look at right now. Again, we're doing the same thing we did for merge sort. We're going to analyze using unfolding, but it'll be a lot less painful. Sort of a unfolding light. Before we get to binary search. So this is the actual analysis of merge sort. So we made the simplifying assumption that n was a power of 2, which made our lives easier, but in reality, n could be any value. So that means these lists are one's going to be slightly bigger than the other in some cases. So how fast does it run in that case? We're not going to go through this. I would probably put you right to sleep, but yeah. In this case now, we're going to make a sort of an inexact guess at a closed form, because it's hard to get it exactly correct if we don't know exactly how it splits. So now this becomes an inequality. Yeah. So we have we would make the same guess essentially, but now proving by induction would be a little trickier. Yeah. So proving by induction, so I could replace this floor with n minus 1 over 2 and this ceiling with n plus 1 over 2, assuming that we're splitting an odd value of n. And then it sort of breaks down like this. So it's very complicated. Well, it looks more complicated than it is. Once you understand a bit about logarithms, you could go through this yourself and prove the closed form, but it does become an inequality. If you're interested, you can check that out or come to office hours and I can explain it, but I'm not going to go over it today. Yeah. But yeah, we get the same thing. We just get an inequality. Okay, so binary search. Here's the binary search algorithm. I have a sorted list of something. In this case, we'll be looking at numbers. Maybe it's scantrons. So I'm going to check the middle item. If that is what we're looking for, then we're done. Otherwise, if the item we found is greater than what we're looking for, then we want to look in the lower half or left half if we're, going from left to right. If the item we found is less than what we're looking for, then what we're looking for is greater, so we're going to search the right half. Okay, so that's the idea. And here's an example. So I have a sorted list of numbers. I want to search for the number 17 in this sorted list. I could just start at the beginning and see, is 1 equal to 17? No. Is 2 equal to 17? No. And I can keep going until I find it. But as we talked about, it might be more efficient to sort of jump into the middle. So I look at 14, I compare it to 17. I know 17 is greater than 14. So what I'm going to do now is I know 17 is going to be somewhere over here. I'm not sure exactly where, but somewhere. So what I can do is I can basically, I know I never have to look here. 17 won't be found there. So I eliminate at least half of my list. Now I take whatever amount of the list is left and I go to the midpoint, right? So roughly speaking, is it better to go to the left or the right, right? So the midpoint, there is no actual midpoint, so we're approximating. If you don't know the distribution, then it doesn't matter. You can go slightly higher or slightly lower than the midpoint. I see that 17 is less than 22. So again, I'm going to concern myself with this section, and I do not have to look here ever again. All right. At this point, I look at the midpoint. It's equal to 17. I found it. I'm happy.
And I used 3 comparisons and a little bit of math, right? I have to compute the midpoint, but that's pretty easy for a computer. And if I had done what I said I would do in the first place, which was the linear search, that would have taken 9 comparisons. Okay. So everybody clear on binary search? Okay, so here is the binary search algorithm. Now this is an actual algorithm, so there's a lot maybe going on here. So this is my list. This is my frozen computer. Okay, so all right, pen's not working. Let me see here. All right. Okay, so I'll do it without the pen. So just to explain this here, that's really not convenient at all. Maybe I need a new battery. It died yesterday too. Okay, yeah, it's probably the battery. Okay, so this here, so I have my list and I have the item I'm looking for, and this is the point of the list. The start of the list, the section of the list I'm looking through, and this is the end of it. So in the beginning, it would be, the very front and the very back. And as we progress, we change these values. If end is less than start, so I'm not going to explain all the details, but this is essentially a list of length 0. Right, so if that happens, I know it's an empty list. I haven't found what I'm looking for. I can simply return. Otherwise, I compute the midpoint. The start of where I'm looking plus the end divided by 2 is the midpoint of that, plus or minus 1. And then I make a copy of whatever I find there. So in this algorithm, we're going to count memory accesses because memory accesses are sort of slow, right? You have to perhaps fetch them from either from RAM, which is, slower than the cache, or from the hard drive. So we're counting this line, the number of times we execute it, which is once per recursive call. And then we compare it to the item we're looking for. If we find it, we return. Otherwise, we make a recursive call on roughly half the list. We're going to do an inequality here as well, because again, it doesn't really divide evenly. Okay, so yes, base case list of length 0, I make 0 memory accesses. Every other case, I make 1 memory access. So that's what we have to remember. And then we can make our recursion. So yes, again, if we have a list of length 0, we simply return. So T of 0 is 0. Again, the T of n is the number of memory accesses in this case that we perform doing a binary search on a list of length n. So our base case, T of 0 is 0. Our recursive case, well, I make 1 memory access per call. So I put the 1 there. And then I make a recursive call, either this recursive call or that recursive call. And in the worst case, it's on half the list. But generally speaking, it's even harder to guarantee that with binary search. So that's why we're using the inequality. Okay, so we have a very simple recurrence in this case, much simpler than merge sort, but we're going to do the same thing. We're going to unfold it until we find a pattern. The pattern is going to be pretty straightforward. And then we're going to substitute in our k value, right? So we assume it goes for k steps. We substitute in our k, solve for k, get our guess, prove by induction. Okay, so using unfolding, well, this would be T of n less than or equal to 1 plus T of n over 2. T of n over 2 is less than or equal to 1 plus T of n over 4, right? It's just half the list again. So I'm going to substitute that in here, 1 plus 1 plus t n over 4. N over 4 is t of n over 4 is less than or equal to 1 plus t of n over 8. Oh, whoops. Yeah, look how close that is. So the pattern continues here. I substitute 1 plus t of n over 8 in for this, but instead of writing it as n over 8 now, I'm going to write that as n over 2 to the power 3. Right. So we can see our pattern unfolding. I have, in this case, in the third step, I have 3 1s and t times n over 2 to the power 3. Okay, so now I can take that and assume it goes for k steps. All right. So now it becomes a little trickier. There's a slight little, so I want to find the base case is t of 0, but this will never, n over 2k never evaluates to 0, right? As large as k is, this is never get to 0. So we're going to stop at 1, and then we're going to look at the next step. So what happens at t of 1 is I do one memory access. I compare that to the item I'm looking for, and then I make a call on a list of size 0, right? So there's nothing left after that. So t of 1 is equal to 1 plus t of 0. T of 0 does no memory accesses. So we have, well, we'll leave it like this, but this is actually equal to just 1. Okay, so right. So once we get down to t of 1, I can rewrite, so let's write this as less than or equal to k plus t of 1, right? And we know that, again, we're going to solve for k, knowing that n over 2 to the power k is equal to 1. But this 1 is equal to 1 plus t of 0, so we're going to write that as k plus 1 plus t of 0. All right, so it's just a little wrinkle in an otherwise identical case to the merge sort. I have n over 2 to the power k is equal to 1. I can perform the exact same steps. This means that n is equal to 2 to the power k. I take the log base 2 of both sides, and I get log of n is equal to k. All right. So k evaluated to the same thing. My recursion tree in the binary search is log n. The difference is how much work I do at each call. I only do one memory access per recursive call, and I only do one recursive call for every other, it doesn't, I don't have that branching factor. So I substitute this in for k. Am I gonna run out of time? Just about, but k is equal to log of n. All right, so I get my guess at a closed form is t of n is less than or equal to log n plus 1 log base 2. To prove, then I just prove it using induction, same thing, a little bit simpler. I have my 2 base cases just in case I need either one, and I have my recursive, and I have my guess at a closed form. So in my base case of, which one do I do? T of 1 is less than or equal to 1 plus log of 1, right? I'm simply substituting 1 in for n. Log base anything of 1 is equal to 0. So this is simply equal to 1, which is what we figured out before, right? So that is our base case. Our inductive hypothesis, I assume this closed form is true for any value less than n. And then I plug that into my, here, let's I plug that into my my guess. Or sorry, not my guess, my recursive. Yeah, this one. T of n over 2. Okay, so I plug in 1 plus log of n over 2. This is equal to 1 plus 1 plus log of n over 2. Right, so this is now equivalent to this. I know from what we talked about with the logarithms, this is equal to 1 plus log of n minus log base 2 of 2, which is 1. This one and one of these cancel out, and I get 1 plus log base 2 of n, right? Which is what I wanted to show. So by induction, my binary search is 1 plus log base 2 of n, which is pretty fast. If it's a million things I'm looking for, I look at 20 things to find what I'm looking for, or give up and say that it's not here. Okay, questions? All right, so that's it for recursion. Here is roughly the things that we've learned. So you should know how to prove a closed form of a recursive function using induction. We've done that about half a dozen times. We've looked a lot at the Fibonacci sequence. So there's a bunch of problems that you can map to this recursive Fibonacci sequence. There's a bunch of problems that look sort of like a Fibonacci sequence where we have more than one recursive term. How to analyze a recursive algorithm by finding a recursive function, right? Also how to prove it's correct. So if I give you a recursive algorithm, you should be able to prove that it's correct. Again, it is induction. We've sort of talked it through informally, which you can do as well, as long as you have all of the steps. You need a base case, you assume the recursive case works, and you use the recursion to reconstruct your solution. Then you're proven it's correct. And then using unfolding on a recurrence to find a closed form. So it's a short chapter, but so yeah. Next week, we will get to probability, which is, where probability is lots of fun. I like probability. There's lots of interesting stuff that happens there. But yeah, that's it for today. Any questions? All right. I will see you guys next week.